Hi, my name is Liam Taylor-West. I'm a composer currently working with mathematicians at the University of Bristol. In the last video, we created periodic, deterministic sequences by travelling in a straight line over a fixed grid of squares and writing down A or B every time we crossed a horizontal or vertical line. We began at a crossroads and passed through other crossroads as we continued along our path. The period of the sequence that our path created always ended as we hit a crossroads. So I'm wondering, what would happen if our path never hit another crossroads? Would that create a sequence that was aperiodic? If so, this would be what I've been looking for. An aperiodic sequence created using a deterministic system. A sequence that never repeats, but where we could predict what comes next as the sequence grows. To make sure we never hit another crossroads, we're going to have to choose our path really carefully. Before, we chose our paths by counting up a number of squares and a longer number of squares to reach a crossroad point. This path could be represented as a fraction, with the number of squares we went up being divided by the number of squares we went along. For a path that travels one step up and two steps along, the fraction would be 1 over 2, which is a half. And if we look closely at the point that our path crosses the first vertical line, we can see that it crosses it exactly half a square higher than its starting point. Let's draw a few more paths and see where they cross this first vertical line. A path created from counting 3 squares up and 4 squares along crosses the line 3/4 of the way up the first square. And a path created from counting 2 squares up and 3 squares along crosses the line 2/3 of the way up. These are simple fractions, but even paths that cross the first vertical line at points that represent much more complicated fractions, 89/100ths for example, will create periodic sequences. To find an aperiodic sequence, we're going to want to follow a path that avoids all these periodic ones and find a number that can't be written as a fraction. What sort of number would that be? Mathematicians call numbers that can't be written as fractions irrational numbers. And one of the most famous irrational numbers is the golden ratio, which is often represented using the Greek letter phi. The golden ratio is roughly 1.61803398875, but you can't write the golden ratio exactly as a decimal, because the numbers after the decimal point go on forever and never repeat. The numbers after the decimal point form an aperiodic sequence. Importantly, you also can't write the golden ratio as a fraction, with one whole number divided by another. The two paths we can take that use the golden ratio are the one where we move along one square and up one golden ratio amount of squares, and the one where we move up one square and along one golden ratio amount of squares. If we look along this line, we can see that we have managed to avoid all the crossroads, meaning our sequence should be aperiodic. Let's see what sequence this path creates. The sequence would continue for as long as you travel along your path, but let's stop it there. Looking at the sequence, we can see that there is no way to break it down into a smaller repeated chunk or period. There are a few sections of the sequence that look like they might form a period, but the sequence will always eventually change and break the pattern. Even really long sections like ABAABABA don't work. As we hoped it would be, this is an aperiodic sequence. Before we look at the sequence more closely, let's try and make some music out of it. The first time I saw this sequence, it reminded me of a drumming pattern that you're taught when learning to play the drums, called a paradiddle. A paradiddle follows a periodic sequence that tells you to play the drums using your left or your right hand in this pattern. Right, left, right, right, left, right, left, left, right, left, right, right, left, right, left, left. Our aperiodic pattern looks like a complicated, never-repeating paradiddle with A's and B's instead of L's and R's. Let's try and play our sequence as if it was a drumming pattern. Choose a different sound for A or B, or assign A and B to your left or your right hand, like in a paradiddle. It might help to break the sequence down into smaller sections of 8 beats, the same length as a paradiddle, like this. To make it easier to play, some of these lines are repeated. The first line is the same as the second line, and the third, fourth and fifth lines are also the same. I'm going to play A's with my left hand and B's with my right hand. So, we created this sequence by travelling in a straight line over a grid of squares. Because there's no randomness involved in this process, we can call it a deterministic system. Deterministic systems have rules. So what are the rules that create this sequence? Is there a way we can create this sequence without having to draw a perfect golden ratio line over a grid of squares, which is pretty much impossible without a computer? Let's just take the very start of the sequence. It begins with 2 parts, A and B. To grow the sequence, you can take the first part, the A, and add it to the end of the sequence you already have. So AB plus A equals ABA. Although the sequence is 3 letters long now, you can still think of it as being in 2 parts. The part we started with, AB, and the part we added on, A. So let's add the first part, which is AB, on the end again. So ABA plus AB is ABAAB. Now we have a sequence that is 5 letters long, that can be thought of as being made up of the part we had before, ABA, and the part we added on, AB. So let's add the first part on the end again. We can keep doing this to make the sequence longer and longer. This rule is really simple to follow at first, but the more times you repeat the process, the longer the section of sequence you have to add on the end becomes. Very quickly, this becomes a huge amount of information. Have you ever played the market game? The first person says, I went to market and I bought apples. The second person says, I went to market and I bought apples and bananas. As the game continues, the list of items you need to remember grows. Our sequence grows in a similar way to this, except the market is only selling 2 items, apples and bananas, nothing else. And the amount of information you need to remember grows much more quickly. For example, the first person says, I went to market and I bought apples. The second person says, I went to market and I bought apples and bananas. The third person has to buy what the second person bought and then add on what the first person bought. So they say, I went to market and I bought apples, bananas and apples. The fourth person has to say, I went to market and I bought apples, bananas, apples, apples and bananas. When your shopping list contains only 2 items, the order in which they appear becomes much harder to remember. If a class of 30 students is playing the original market game, the 30th student would have to remember a list of items that is 30 items long, which is already pretty tricky. In our new version of the market game, the number of items the 30th student would have to remember is 1,346,269. Why don't you try building this sequence step by step for yourselves? You could write it on a piece of paper, you could build it using coloured blocks, or see how much of it you could memorise. Something that I'd like us to quickly look at is the number of A's and B's that appear in our sequence as it grows bigger step by step. When the sequence is 13 letters long, there are 8 A's and 5 B's in it. If you divide the number of A's by the number of B's, 8 divided by 5, you get 1.6. The next chunk of the sequence has 13 A's and 8 B's in it. 13 divided by 8 is 1.625. The next chunk has 21 A's and 13 B's. 21 divided by 13 is 1.61538, and the numbers after the decimal point just continue. But what do you notice about these numbers? If you took a really, really long section of the sequence and divided the number of A's by the number of B's, what number do you think you'd get? I'm not sure if you worked this out, But as the sequence gets longer, the number of A's divided by the number of B's gets closer and closer to the golden ratio, the number we use to create our path over the grid of squares. There are lots of other interesting things about this sequence. One of them is that it is an example of a self-similar fractal. Self-similar fractals are objects that contain smaller versions of themselves if you zoom in and look at them more closely. You might have heard the word fractal before. Here's Elsa singing about fractals in the song Let It Go from the film Frozen.
We saw this spiraling in frozen fractals all around.
What does Elsa mean when she says frozen fractals? She's talking about snowflakes. Snowflakes are an example of fractals occurring in the natural world. If you look at a snowflake, you can see that each arm has smaller arms branching off it, and those arms have smaller arms branching off them. So, what about our sequence? In what way could our sequence be described as a fractal? Well, why don't we see what happens if we let this sequence control our movements? Let's do what we did in the last video and replace every A of the sequence with the sound of a kick drum and every B in the sequence with the sound of a snare drum. What if we listened to this pattern on headphones, went for a walk, and let the pattern control the journey we took? If you walked with each step in time to the beat, and if you changed direction every time you heard a kick drum, turning left if the kick drum landed with your left foot, and right if it landed with your right foot, you would follow this path. Imagine that you have a route tracking app installed on your phone, and this is the path it is drawing based on your journey. At first it doesn't make a lot of sense, but over time it starts looking like our path has some form of organisation to it. If we keep going for a really long time, we can see that our path is forming a fractal. The shape of this large section of our journey is the same as this smaller section of our journey within it, and this smaller section within that bit. This is an example of a self-similar fractal, and we have created it just by listening to our aperiodic sequence. So, is there a way of representing these fractal qualities in the music we make from this sequence? Let's start by looking at this section from the start of the sequence. When we built the sequence from scratch, we started with two chunks, A, B and A. Because everything after this was created by combining sections of the sequence that had come before, our sequence can be completely broken down into those two chunks of A, B and A. Let's colour them in yellow and blue. What order do the yellow and blue blocks appear in? If we name the yellow blocks A and the blue blocks B, then we can see that this is a stretched out version of our original sequence. Our sequence contains within it other versions of itself, just like the self-similar fractals we've looked at. We can repeat this process again and again and find even more stretched out versions of the sequence within each new sequence. You might have noticed that the length of A's and B's is changing as we keep stretching out the sequence. In the original sequence, A's and B's are the same length. In the next sequence down, A's are 2 times as long as B's. In the next sequence down, A's are 1.5 times as long as B's. If we keep going, we will eventually get to the point where A's are exactly 1 golden ratio times as long as the B's. This matches the 2 steps we took to choose our path over the grid of squares at the start of this video. To me, these stretched out versions of the sequence, layered alongside the original, look quite musical. So let's try performing them. As our original drum pattern plays, let's choose 2 new sounds to be A and B of the first stretched out sequence. Every A is 2 beats long, and every B is 1 beat long. Let's add the next sequence with 2 new sounds. Every A is 3 beats long, and every B is 2 beats long. If we add another layer, the A's will be 5 beats long, and and the B's will be 3 beats long. And we can keep adding more and more layers as we keep adding more stretched out versions of the sequence. Why don't you have a go at performing this rhythm as a group? The ideas we've looked at in this video series are based on current research being done by mathematicians at the University of Bristol. Aperiodic order, as the study area is called, is a really fascinating subject with growing popularity and several questions left unanswered. One of the really amazing things which relates to aperiodic sequences is what's called aperiodic tilings, which is something we'll have to look at another time. Thanks for joining me. Goodbye.